important is not anything other than the sequence of insertions. So as long as we choose the right values, they will just make a balanced tree. It's really cool. It just happens automatically. Or I should say automatically, right? So, so we're going to say if A is less than or equal to B. And of course, else means do nothing, right? Else means do nothing. I don't even need to have it there. I just do it because students like it. I need to have an else. Why? If it doesn't do the if, it's just going to finish. That's okay. So if A is less than or equal to B, that means we have at least one node. So we need to find the middle node. Where's that middle node? So the middle node M is equal to B minus A divided by 2. Are you with me? Okay. So else, I'm going to say here, do nothing. Okay, so if A is, so middle is going to be here. And then what are we going to do? We are going to insert. So we're going to say, and I guess we need the tree here. So this is the tree. So this is the tree. So the root gets passed in and we call it tree. And then what we're going to say insert, or we're going to say, let's use some object-oriented type language. We're going to say tree, insert, array element A at index M. Yes? Now what are we going to do? So we inserted the middle element because there is a middle element. What do we do next? Quickly. Time's running out. Yes, now we're going to recurse. Sure. Now we're going to go build balanced tree using the same array, using the same tree, but now we're going to recurse with the left side of the tree, which will be denoted how?
n-1.
So the beginning will stay the same, and it's going to be n minus 1. And then build balanced tree, excuse me, A, and then we're going to go and that's it. Now what's the complexity of this? Well, clearly this is a single statement. So you can say theta 1. We could say T of n is equal to, so that's the recursive cost. Can you tell me how to write that? How do we write this into the recursive cost? T of n is equal to? Go ahead. 2 T How are we reducing the problem? And over 2. Because basically these are taking the left side and the right side of the array, so roughly the reduction is in half. Actually, it's a little bit less than that, isn't it? Because we've taken one out. But it's good enough. So now, but plus, oh, this is a tough one. This is a tough one. Plus what? Plus the actual cost. Well, the actual cost here is only theta 1 here, but this is tree insert. That's a problem. Because, how do we count the complexity of insert? Well, inserting a root, we're going to say is free. Pointer is null, set it. But when we do this, now we have to compare once, compare once. When we insert the next one, we compare once, compare twice. Compare twice, compare twice, compare twice, compare 3 times, compare 3 times. We have to sum all those comparisons. So every node has a different insertion cost. We'll come back to this. Okay, so that's kind of what I want you to be thinking about a little bit. All right? But, well, actually you don't. Well, I have some more interesting things to say about trees. And remember how we talked about the average quicksort complexity last time? It turns out that trees, binary search trees, have the same exact behavior as average quicksort instruction counts. They're the same. Building a balanced or a full tree will have the same complexity as quicksorting n elements. Inserting n elements to produce a full tree is exactly the same as quicksorting n elements on average. Let me say it again, because I'm saying it wrong. Since this is on tape, you're going to say, well, what's he saying? Okay, so we know what average complexity of quicksort is. Random data, quicksorted, average complexity is 1.38 n LGN. It turns out that if you take random data, forget about this, if you take random data and you insert it into a tree, you're going to get a tree of a general shape. We don't know what the shape is going to be, because the shape will be driven by the sequence of insertions, and the sequence of insertions will be random. The tree will have an exact relationship in terms of some of its properties to the quicksort. And I'll get to that next week.